Okay, so now we're on lecture 3 for this probability review. And today we're going to cover expected value. So here, the expected value, so now we have worked up the what a random variable is and its distribution function. And the expected value in simple terms is just the average, a weighted average of the possible values that the random variable can take. And it's the first kind of particular information of the random variable that kind of tells you what's the expected value this random variable will take. And it really means that if we have this analogy that a random variable x is a measurement, the expected value is going to be the average value of the random variable over a long time if you make these measurements repeatedly. Then if you average the outcomes of these measurements repeatedly, the the average values that you get are going to tend to this expected value. And this is the what people call the law of large numbers, and this is the intuition behind expected value. It's a weighted average of the possible outcomes of a random variable x. And here we have the formal definition. So we take a random variable x, RV, random variable, and we define the expected value of x and denoted by e of x to be the weighted average of the outcomes of x. And here we have e of x, and you'll see often that mu of x, that the expected value for random variable is going to be denoted mu of x. And in the discrete case, where the random variable takes values in the integer line, then this is going to be the weighted average. So the possible outcome is x, and you weight it by the probability that this is the probability that x equals x. And if you write this probability, recall that we write this probability with the probability distribution for the random variable x. This is going to be the formula. And then similarly for the random for a continuous random variable, you have this formula which mimics this. And this derivative term seems a little bit odd, or it may not be particularly clear, but what we have here is that this really just stands for the probability of I think really this should be dx. This should really be this. And this really stands for the probability that x is between x and some x plus delta x. So for a small interval, so this is really kind of a Riemann sum. But really, so this is breaking up the real line into small intervals and weighing this outcome with this probability of the probability that x is in this small interval between x and x plus dx. And using the probability density function, this is going to be the formula. So this is going to be our formulas for expected value, and the interpretation is that the weighted average of the outcomes. And in the idea of the picture that you should have in mind is that the expected value really is a center of mass. And this is an interpretation that's also useful for probability, that a probability function really is telling you like a proportion of mass in a certain region. So here we have that probability that x, we have this random variable with two outcomes, A and B, and the mass at each position is proportional to the probability. So this is a high probability outcome and this is a lower probability outcome. Then the expected value is going to be the point where this seesaw is balanced. So it's going to be the center of mass. And this is what we want to think of as the expected value, a weighted average. So in here, since this value has higher weight than the center of mass is going to be closer to it and further away from this. So this is the rough idea that we should have of expected value. In the next couple of slides, I'm just going to do some computations for the expected value. And here, for some, I think, just continuous distributions, the computations are similar for discrete, but I'll just focus on continuous. And here we have the formula for the expected value. And in the previous lecture for the uniform distribution here on A, B, we said that the distribution is going to be equal to 1 over B minus A for X between A and B, and 0 otherwise. So after plugging that in here, we see that this interval from R, we actually integrate only from A to B because it's 0 otherwise. In particular, A to B is the support of this density function. And this is the only region where the random variable takes possible values. And then we have this X comes here, and then we just integrate. And then the result is B plus A over 2, which by looking at the picture, we again have this seesaw where now we have mass equally distributed throughout the seesaw, and it's symmetric, and we just find the halfway point, A plus B over 2. So this is going to be the expected value. Let's move on to now the Gaussian distribution. This integral, again, is a little bit more, this integral will now be a little bit more involved. So in here now we have that the density function is given by this function, by the normal distribution. And we just plug this f of x and integrate. And here the support, again, is the whole real line. So the integral does go from negative infinity to infinity. And we could potentially compute this using U substitution. And I forgot to add details here. This is 2 sigma squared. Or maybe I just erased it. I don't know. But 2 sigma squared. But we can, going back to the computation of this integral, you can do a U substitution. U is equal to, U is equal to x squared over 2 sigma squared, and then compute it. But if we go back to the interpretation of the seesaw, of the center of mass, it's clear from the definition of the density function that the density function is symmetric about the point 0. And so if we put the center of mass here, we'll see that the seesaw will be balanced. And just by symmetry, we can claim that the mu of x, the expected value, is going to be 0. And this is an important lesson because a lot of times the formulas in probability, like expected value, variance, conditional probability, and so on, we have formal definitions as summations and stuff like this, but these formulas tend to be difficult most times, unless their examples are really easy. And most of the times we need some extra machinery to actually help us get the solutions. And a lot of times it's symmetry, noticing a particular symmetry or noticing a particular interpretation to simplify the problem. And we can take shortcuts this way. And in this class, I do encourage you to try to think about symmetries or shortcuts, or try to interpret the problem probabilistically. And this is really the art of probability, trying to find arguments such as symmetry to simplify the computations. And if you go on and study more probability theory, this is still a theme of research nowadays, whereas now people are trying to find symmetry from more sophisticated algebraic structures. But here we see symmetry coming in and helping us solve this. So in here, I don't really have to bust out my calculus book to compute this. I can just look at the picture. Now, let's look at the exponential case. And here we have x being exponentially distributed. And again, this is our formula for the expected value. The distribution function is given by this for the interval 0 to infinity. Remember that an exponential distribution is interpreted as a random waiting time. It's a waiting time for an event to happen that has a memoryless property. A property where just because you've waited a certain amount of time doesn't make the random event more likely to happen or less likely to happen. So we have this exponential distribution, and since it's a waiting time, the support is just going to be a number from 0 to infinity. It's positive. So these are going to be our bounds, and we plugged in the distribution function. And in here, I want to tell you that there is a simple way to just see it from the picture, but not really. This actually, you actually do have to do integration by parts. And I didn't do the computation here because I already know the answer, and I just plugged it in there. Maybe you want to Wikipedia this and double check this because I just kind of did it from memory, but I'm pretty confident that that's true. And here, what this is telling you, if we have this interpretation that the exponential distribution is a random waiting time, this is saying that typically, on average, if your parameter is lambda, you're gonna wait 1 over lambda amount of time before the event happens, typically on average. So in here, I was just thinking that you can even figure out in terms of units. So if the units of x have to be time, the units of lambda x have to be dimensionless, then the units of lambda is going to be 1 over time, meaning that the dimension of 1 over lambda is going to be time. So just by this dimensional analysis, this is a way to remember that this is the expected value. So this, if x is a random waiting time, which the units are going to be time, the expected value should also have units of time, and we see that from this dimensional analysis that 1 over lambda is going to be time. So this is going to be the average waiting time. And this is a quick way to remember that it's 1 over lambda instead of lambda. Because whenever I see the parameter lambda, I don't necessarily remember the answer, but I do know that it's lambda or 1 over lambda. And this, I can pick this one out by the units. Now, in here, I actually have the discrete case, the distributions. And in this case, I just went ahead and computed the expected values from the definition. And in here, let's start with the uniform distribution, which should be similar to the uniform distribution in the continuous case. This is the summation that we end up making. And at the end, the solution is n plus 1 over 2, which is essentially the halfway point between this, the halfway point of this interval, which you can do that by symmetry. You can figure that out, that it's n plus 1 over 2. Or in here, you can use this series formula for the sum of consecutive numbers. And both this, you could argue that using a probabilistic argument that you can figure out this summation formula using a probabilistic argument. You can just say that this is equal to this due to symmetry, and then this would imply that the summation of x is equal to this. but this is a valid way to prove certain things. Now let's look at the binomial distribution. And here we have this expected value. The summation turns out to be this. And here you actually need a little bit of machinery if you want to do the explicit summation to find the value of the summation. And in particular, you need to use the binomial theorem, which says that 1 plus alpha, or rather, let's say alpha plus beta to the n is equal to the summation of n choose k to times p to the k times 1 minus p to the n minus k. K from 0 to n. And this is not quite this summation, but if you take the derivative of both sides with respect to p, then you would get it. But, and I'm not going to go through the details, but it's this. This result comes from this binomial theorem. So the binomial theorem is this. Now let's do the geometric distribution. X is geometrically distributed, and here this is the summation we have to do. And again, to do this summation, we do need a geometric series, and it comes from this formula: r to the k from k 0 to infinity is equal to 1 over 1 minus r, and here r absolute value is less than 1. And then you take the derivative and obtain this result. Yeah, here, oh, sorry. Yes, that should not be P or Q. I knew there's something funny with this. This should be alpha to the k, beta to the n minus k. And then you obtain this result by taking a derivative with respect to p, and then multiplying by p. So this is the discrete case, and on top of just having the answers or having the expected values for this random variables, what I want to point out in all these computations is that you do need some machinery to compute this expected values. And this machinery is now standard tools in mathematics, series formulas, binomial theorem, geometric series. This is all stuff that you learn in high school and undergrad, and everyone's familiar with it. But at some point, people needed to develop this theory. And again, in modern probability theory, this is still the theme of developing machinery to compute certain probability functions or expected values. Now, I want to talk about a few properties, or the main property of expected values, which is linearity. And here, if we have a pair of random variables, x and y, and alpha and beta, two real numbers, then we have this property that alpha x plus the expected value of alpha x plus by is equal to alpha times expected value x plus beta times expected value y. Or equivalently, we can break up this identity into two parts, meaning that this is a scaling, that if you scale the expected value by x, you can take the scaling out of the expected value. And if you take the expected value of the sum of two random variables, then you can take the summation outside the expected value for any two random variables, and this is for any random variable and any alpha. So this is the main property, and this simplifies a lot of expected value computations. And this is equivalent to this too. And here in a few slides, I'll actually prove this statement. And this is not very difficult to prove, and if you're uncertain about it or you don't quite remember the proof, try to go through it by yourself. So here, I just wanted to show an example where this linearity actually helps out. And here, I'm going to take a collection of random variables labeled by k, that have a Bernoulli distribution with parameter p. And in here, xk, recall, is interpreted as a coin flip with probability p of heads. And then I define z to be the sum of x1 through xn. And this is really counting the number of heads in end coin flips. So the number of heads in end coin flips here. And by the previous lecture that we've discussed before, we know that z has the binomial distribution with parameters n and p. And in a few slides back, we actually computed this expected value, and the expected value of the binomial distribution we computed to be np, and we used this formula. But alternatively, we can use linearity, and we can use linearity to split up the expected value into each component of x1, x2, all the way to xn, and then we just need to compute the expected value of each of these. And here the computation is pretty straightforward. It's the average of two numbers. One of them is 0 and the other one is 1, and you see that the expected value of xi is equal to p. So for each one of these numbers, you have that this is p, p, and p. So you have that the expected value is np. So we see that here, using linearity, we can simplify the computation of the expected value. So by linearity, it's a sum of p's, or using the definition, this is going to be the binomial theorem. So we see the trade-off here and using the properties of expected value. So always keep in mind linearity. It'll simplify your computations. Now, let's wrap up with variance. And give me 1 second. Where's the proof of linearity? Oh, you know what? The proof of linearity will actually come up next lecture. So hold on tight for this proof. Instead, now we're gonna move to discussing variance, and I'm holding off giving this proof for this because we need to discuss how to compute the expected value of two random variables. And here I've only given you how to compute the expected value of one random variable at a time, but nonetheless we can use the property. Now let's talk about variance. So we have x, a random variable, and we define variance x by this formula, and it's the expected value of the difference between x and its expected value squared. So, and here using linearity, this is a fun exercise if you haven't seen it before, but using linearity, you can actually show that this expected value is equal to this formula. And we should have the square right there. And really, what this random variable is measuring is the distance away from the expected value. And you square it so that the distance is always positive. So this variance really is measuring the distance from the expected value, and it's gonna give it a positive weight either if it's positive or negative. So this is really measuring the variation from the fluctuation from the expected value. And it has this straightforward formula. And here I just wanted to point out two extreme cases of how the variance could look. And in this example, which I should probably say maybe example. In this example, we're looking at two extreme cases, and I wanted to engineer these two cases so that there are two random variables, and in here we have two random variables, both that have expected value mu. So in here, both are expected value mu. In this random variable, I'm putting all the mass on top of mu. So this is clear that the expected value is mu. And in this other example, I have the mass equally distributed a distance a away from the expected value. But it's an equal distance from mu. So we have that if we spread out independent of a this way, with equal mass on both sides, that the expected value is going to be mu due to symmetry. So here we have that mu is going to be the expected value for both cases. But in this case, we have that the variance is equal to 0. So this quantity, the x minus the expected value, in here, this is always going to be 0. So we're going to have that this is 0. Now in the other case, where we start spreading the mass apart, we see that the variance is going to be a squared. And this is just an extreme case where you can see that you can, for any expected value, you can have an arbitrarily large variance. And really what we're measuring with this a squared with the variance is how far apart can the mass be away from the expected value. And it's always true that if the variance is 0, then this means that all the mass is going to be centered at mu. So the smaller the variance is going to show that most of the mass is centered near mu. And the larger it is, means that the mass is centered away from mu. So this is a quantity that measures or gives you an insight into how the mass fluctuates around the expected value of the random variable. And moreover, if the variance is 0, then there's no fluctuations, so it's deterministically mu. And this is it for this lecture. This is lecture 3, expected value. It's just the main idea is the formulas to compute expected values, and the theme of expected value, the idea that you should get across, is that an expected value is a weighted average. And it's try to think about it as a center of mass, try to interpret probability distribution or probability densities as a mass function and a distribution of mass along the integers or along a real line. And then this expected value is going to be a center of mass for this distribution of mass, which is the probability function. And linearity is always fun. So let's call it a day, and I'll see you again for lecture 4, joint density.